Hi, I'm Sandeep. I'd like to introduce our article High Integrity Measurement Error Time Correlation Modeling for Safety Critical Navigation. Safety critical navigation applications, like in aviation, require high integrity measurement error models. We can use overbounding theory to derive probabilistic error models for snapshot estimation, which combine measurements from a single instant in time. Uh, on the other hand, time sequential estimators can improve performance, but such estimators require high integrity measurement error time correlation models. In this article, we propose two new methods to derive such models. Current time correlation modeling methods derive first-order Gauss-Markov process models through ACF bounding. ACF, which is shown here, is the expected value of two measurement errors separated by a lag time tau, and FOGMP ACFs are decaying exponentials, and here we are showing the sample ACFs in gray, and these sample ACFs cannot be enveloped by FOGMP ACFs, especially for large lag times, and outliers can push the model to be more conservative. Instead, in our approach, we focused on lagged products. Lagged products are shown here for 2500 independent FOGMP time series, and which we can see do go below zero, and the expected value of this random variable is the ACF. And in this work, we derived the PDF of the first order Gauss-Markov process lagged products, and we use this in CDF overbounding of lagged products. So how does our approach work? We first compute the empirical CDFs of the measurement error lag products, shown here on the right, and we compute the FOGMP lag product CDFs by integrating the PDF we derived, and we find the FOGMP model parameters such that the sample CDFs are bound for all the lag times of interest. And using our theorem that CDF bounding leads to a bound on the mean, which is the ACF, this gives us the time correlation model. Certain applications frequency domain methods are better suited. Currently, PSD bounding is being used to derive models, but PSD bounding suffers from the same issues as the ACF bounding. So instead, we focus on overbounding the scaled periodograms. And in this paper, we derive the theoretical distribution of the scaled periodograms of FOGMPs, which allows us to derive models in frequency domain. And we use the same procedure as we used in time domain to derive the frequency domain models. We apply our method to iono-free code minus carrier data collected over a day, which is representative of the GPS multipath error. And in this paper, we show how we process the data for model identification. Here are the models we derived for the data using the two methods, and these plots shown here visualize the margins between the sample and the model CDFs as a function of lags and frequencies. In the article, we describe how we derived these models. Here is the summary of our article. Thank you for your attention.